Hi students, now we are going to derive a remarkable equation in the topic of thermodynamics, that is the Meyers relation. Extremely important derivation for the board exams. Now what is that Meyers relation? I have already told you, my dear students. For solids and liquids, the specific heat capacities will be fixed. That means the solids and liquids have only one value of specific heat capacity, while the gases have infinite number of specific heat capacities. Among the infinite values, all are not significant. Only two are very significant. And those two specific heat capacities for a gas are called as the molar specific heat capacities, or the principal specific heat capacities, namely Cp and Cv. Okay, what is Cp? It is the molar specific heat capacity of a gas at constant pressure. And Cv means what? It is the molar specific heat capacity of a gas at constant volume. And we have already studied that Cp is greater than Cv, and this difference between Cp and Cv is equal to the universal gas constant, namely capital R, and its value is the same for all gases for 1 mole. So for 1 mole of any gas, what is the value of this constant R equal to? It is 8.31 joule per mole per Kelvin. What do you mean by this? It is the quantity of heat required to raise the temperature of 1 mole of a gas by 1 Kelvin. It is the same for all gases. So this relation Cp minus Cv is equal to R we are going to derive in 2 steps. Okay students. Now initially I will consider 1 mole of an ideal gas. So I am going to consider 1 mole, for example, of an ideal gas taken inside a container, a cylindrical container always we will consider. And you can see that except the bottom of the cylinder, the walls of the cylinder are insulating, and the frictionless, smooth piston is also insulating. It's also provided with the handle. So this type of cylinder is having a conducting base. So the base is purposely made conducting for a provision to the flow of heat from the surrounding into the system. Okay. Now in the first picture I have considered 1 mole of an ideal gas whose initial pressure is P, initial volume is V, and initial temperature is a capital T Kelvin. I have not supplied any heat to the system. So in the first picture, this is the initial status of the system which we have considered. Okay. Now to derive the Meyers relation, I am going to perform this derivation in 2 steps. So the first step, okay, step by step if you learn means it will be comfortable for you while learning. So what is the step 1? In the step 1, it is performed at a constant volume, okay, at constant volume. This is the first step. So you can look at the picture here, the second picture for the first step, okay. So I am going to supply some heat. I am going to supply some heat to the system through the conducting base. So you see here, I am supplying some heat, namely Q joule. So Q joule of heat is supplied to the system by keeping the constant volume, is it not? That means the gas should not be allowed to expand. The volume should remain constant. So how it can be achieved? I should not allow the piston to move. That is very important. I should not allow the piston to move upward. So I take some 2 screw or bolt, and I will fix this piston on both sides like this. So using nut and bolt like this, so I have fixed the piston such that the piston is rigid. The piston cannot move now. Okay, when the piston cannot move, the gas cannot perform work. Okay, if the gas cannot perform work means what for the entire quantity of heat supplied must be utilized. Now this quantity of heat will increase the internal energy of the system. So the pressure will increase and the temperature will increase, but the volume remains constant. That is the first step. So it is performed by keeping the volume as constant. So now initial pressure was P. Now the pressure increases from P to P plus dP. And the volume is constant. Volume remains constant. And the temperature increases from T to T plus dt. Is it not that? So for this, how much quantity of heat is supplied? So this is quantity of heat supplied Q must be equal to 1 mole, okay, 1 mole into the specific heat capacity at constant volume multiplied by dt. Is it not? By definition, what is CV means? CV is the molar specific heat capacity at constant volume. Is it not? So this is CV is the quantity of heat required to raise the temperature of 1 mole of a gas by 1 Kelvin. But here what is the change in temperature? Instead of 1 Kelvin, it is dt Kelvin, dt by dt. The temperature has increased by an amount dt. So for dt Kelvin, the quantity of heat supplied must be equal to CV into dt. And now the work done is 0 here, is it not? So since the volume is remaining constant, W is equal to 0. Therefore, from first law of thermodynamics, so from first law of thermodynamics, the first law of thermodynamics states what? Q is equal to change in internal energy of the system plus W. Is it not? So here W is equal to 0 means Q must be equal to what? So this is equal to du. So the quantity of heat supplied Q is equal to CV into dt. Also from first law of thermodynamics, the quantity of heat supplied is equal to du because W is equal to 0. So combining these two, so I will take this as the first equation and this as the second equation. So comparing equations 1 and 2, therefore I can write now this du, okay, du is equal to CV into dt, CV into dt, okay. So this is another equation. So I can call this as equation number 3. So the change in the internal energy of the system is equal to what is CV into dt. So this is in the first step. Have you all understood the step 1 first of all? Okay. Now the second step I am going to perform. So whenever I want to go to the second step, I should bring the system back to the original or initial conditions of pressure, volume and temperature. So at the end of the first step, now I will again stop this source of heat and I will allow the system to cool down and let it come back to its original conditions of pressure, volume and temperature. Okay, system is restored to its original condition. I will write here. Okay, system is brought back. Okay, it is brought back to the initial pressure, volume and temperature. It is better if you write this statement, then only you will understand. So once again we are going to start the step number 2. From where? From the initial conditions. From the initial conditions of pressure, volume and temperature. So I am going to write here step 2. So this is step number 2. So in the step 2, what I am going to consider is pressure as constant. Okay. So the step 2 is performed by keeping the pressure as constant. Now the volume is allowed to change. Volume is allowed to change. Only the pressure is kept as constant. And let us take that the pressure P is equal to constant. And volume changes from V to V plus dV. And the temperature also must increase from T to dt. The same rise in temperature as in the first step. By the same amount dt, the temperature should be allowed to increase in the second step also. Understand? But here the volume is allowed to increase. That means what? The piston is moving upward. You can see that the initial position of the piston is here and it is moving upwards. So that it is exerting a force, and A is the area of the piston. So that now the piston is moving up through a small distance dx. So when the volume is allowed to change, definitely the piston is moving upward, volume has increased, the gas has performed some work. Now, if you supply the same quantity of heat as supplied earlier, as supplied in the first step Q joule, for the second step also if you supply the same quantity of Q joule, can work also be done in addition to the rise in temperature dt, you tell me? Certainly it is impossible. Suppose you say that here Q is equal to 1000 joule. This totally 1000 joule is utilized in increasing only the temperature of the system. No work is done. For the same 1000 joule, if you supply here also, work may be done, temperature may increase. But can you expect the same rise in temperature here also? It is not possible. So what do you expect in second step? We have to supply some quantity of heat, and for this quantity of heat, I want the gas to perform work. And also I expect the same rise in temperature. Means naturally I should supply a quantity of heat greater than Q, is it not? That idea are getting? So if suppose you take a servant maid in our home is performing washing of clothes every month, and for that the salary paid is 2000 per month. From the next month onwards, if you give additional work to be done, in addition to washing the cloth, you have to wash the vessels also in the kitchen. Can you expect that the maid will expect the same salary? For the same salary, she cannot perform two different works. She will demand more. Physics is everywhere. You should learn from all examples in nature. So, my dear students, in the second step, since the pressure is kept constant and the volume is allowed to expand, for the same rise in temperature dt, we have to supply the quantity of heat more than Q. So I will take the symbol here. The quantity of heat supplied in the second step is Q dash. Okay, how do I perform this? By keeping the pressure as constant. How? For that also one idea is there. How I am going to perform this? By keeping the pressure as constant. So for that I will keep some weight or load, slotted weight I will keep over this. Slotted weight of half kg or 1 kg. Some slotted weight I will keep over the piston. So that always the weight of this slots will be exerting a pressure in the downward direction at a constant pressure. Understand? So the pressure exerted by the external load on the piston will be constant. So when you heat, the gas is now expanding and it pushes the piston upwards against the constant pressure. So here the rise in temperature is dt and the work is also done by the gas. Understand? So in the second step, naturally the quantity of heat supplied is Q dash. And certainly it must be greater than Q, have you understood? And this is now equal to 1 mole into specific heat capacity at constant pressure into the rise in temperature dt. Is it not? Okay. Now, this quantity of heat Q dash from the first law of thermodynamics, it is utilized to increase the increase the temperature of the gas or change in the internal energy of the system by dU. The internal energy has increased by the same amount as it happened in the first step. In addition to that, the gas has performed a work by moving up through a distance dx. So this W, okay, so this is the work done, or this is equal to what? du plus P into dV. Because the volume has changed by how much? dV. The pressure has remained what? Constant. Is it not? So it is P dV. And this is the expression for what? Q dash. So this is another equation required for us. So I will number this as equation 4. Okay children, now you see that from the equation 3, the change in the internal energy of the system in the first step is du. In the second step also, by the same amount only, the internal energy has increased. So I can substitute the equation 3 for du in the fourth equation. Understand? So this du is equal to what? Cv into dt. Understand? Also here you can see this q dash also is equal to what? Cp into dt. Cp into dt. So I can write this q dash is equal to what? Q dash is equal to Cp into dt. And this is now equal to what? du plus p dv. So du plus p dv. And instead of du, I am going to substitute what is Cv into dt. So I will write here. So we will write Cp into dt is equal to, instead of du, what I am going to write? That is equation 3. That is Cv into dt plus what is the next term? P into dV. So P into dV. This is one equation. But for ideal gas, from ideal gas equation, okay, the next step is what? From ideal gas equation for 1 mole. For 1 mole, we have already studied that P into V is equal to R into T. For mu moles, you can substitute PV is equal to mu times RT. This is for 1 mole. Okay, from ideal gas equation for 1 mole I have written. Therefore, for mu moles, I will now consider mu moles. So P into V is equal to mu into RT. This is for mu moles. Okay, now the pressure, volume and temperature are generally called as thermodynamic variables. Now in the second step, volume is a variable, temperature is a variable, because volume changes from V to V plus dV, temperature changes from T to T plus dt by keeping the pressure as constant. Is it not? By keeping the pressure as constant. So if I differentiate this equation, okay, differentiating this equation, P is constant, is it not? P is constant. So pressure is constant, therefore P into change in volume is dV must be equal to mu is constant, R is constant into the change in temperature is dt. Okay, so P dV is equal to what? Mu times R into dt. Okay, one. So this mu R dt can be substituted in place of P dV in the previous equation. This is for mu mole. Understand? So Cp into dt is equal to Cv into dt plus mu into R into dt. For the same rise in temperature, dt can be cancelled. So dt is cancelled on all these two sides. Therefore, Cp is equal to Cv plus mu times R. This is for mu moles, is it not? For 1 mole, okay, for 1 mole, Cp is equal to Cv plus R. Now you shift this Cv to the left hand side. Okay, R Cp minus Cv is equal to R. This is for 1 mole. For mu moles, it is mu times R, that's all. So, Cp minus Cv is equal to R. This only is called as Meyers relation. Understand that? So, this is called Meyers relation, where capital R is called by what name? Universal gas constant, and its value for 1 mole of any gas is equal to how much? 8.31 joule per mole per Kelvin. Now, how did we derive this Meyers relation? Initially, we assumed what? 1 mole of a gas, and that initial pressure, volume, temperatures we noted as P, V and T respectively. Then we performed this experiment in 2 steps. In the first step, the volume was kept constant, quantity of heat was given to the system, and the purpose of this is only to increase the temperature of the gas or the internal energy of the system. So in the step 1, there is no work done by the gas. Why? Because the volume is kept constant. Okay. In the second step, the quantity of heat supplied was utilized for how many purposes? 2 purposes. One is to increase the internal energy of the system by the same amount as it happened in the first step. In addition to that, work also has been done by expanding the gas. So naturally, the quantity of heat supplied at constant pressure must be greater than the quantity of heat supplied by keeping the volume as a constant. This is why Cp is always greater than Cv. One general question is asked, my dear students, in the board exam: why Cp is greater than Cv? So you should mention that the quantity of heat supplied to a system by keeping the pressure as constant, okay, is doing 2 works. One is what? Expansion of the gas, that is by pushing the piston upwards. In addition to that, the internal energy of the gas also increases. While by performing this at constant volume, there is no work done by the gas, only the internal energy of the system increases. This is why Cp is always greater than Cv. And this difference between Cp and Cv is equal to the universal gas constant. This only is called the Meyers relation. I hope you must have understood well. Fine.